Okay, so for those people who are wanting an explanation to my answer, this is it. Because everyone knows that when you have to explain your joke, it's so much funnier that way. Okay, so when we're looking at this, the question says if I pour a root beer into a square cup, would I get a regular beer? So just to talk about some math terms here, when we're talking about roots, that's short for saying a square root, meaning this symbol right here. We call them roots in math because mathematicians are especially lazy and we hate putting the word square in front of our root. So we just call them roots for short. And what a root says is, what number times itself gives me the inside part? Well, when you think about this, what number times itself gives me 9? Well, that would have to be 3. 3 times itself gives me the 9. Another thing that we're talking about here is squaring things, which is the opposite of a square root. If I have 3 to the second power, we call that 3 squared, which just means 3 times itself, which is 9. So what we're saying here is that when I have the square root of something squared, what happens? Well, what's the square root of 3 squared? Well, we've already established that 3 squared, that's the same thing as 3 times 3. It's a number times itself, right? And when I'm saying, okay, what number times itself is 3 times itself? Well, obviously it has to be 3. If you want a better explanation, let's take a look at the square root of 3 times 3 is 9. Well, now I'm saying, okay, what number times itself is 9? It has to be 3. So from this stance, you can see that when I square a root, it looks like they just undo each other. The square right there and the root cancel each other out, and you're left with just a 3. Let's test that with some other numbers. What if I have the square root of 100 squared? Well, that's the same thing as the square root of 100 times 100, which is the same thing as saying, okay, what number times itself is 100 times itself? You can hear it in there, obviously it has to be 100. So from these examples, it looks like you can say the square and the square root will actually undo each other. And in general, that's true. You pick any number you want, x squared, that's the same thing as saying, okay, what is x times x? And then when you take the square root of that, you're saying what number times itself is that number times itself? Well, it would have to be x, to a point. There's a situation where that's not true, and that happens when you square a negative number. So, here's what's going on. Oop, not that symbol, that's summation, that's a calculus thing, wrong thing. Here we go. So let's take the square root of, say, 1 squared. We've already established that's the same thing as the square root of 1 times itself. And when I multiply the inside together, I would get 1 times 1, which is 1. So I'm saying the square root of 1, well, that has to be 1, because 1 times itself is 1. The problem runs into what happens when I throw negative numbers in here. Well, now I've got negative 1 times itself. Negative 1 times negative 1, there's a problem here. That still ends up being a positive 1, because a negative times a negative is always a positive. You've got the positive here. And the square root of positive 1 is just regular 1. So if I were to go back here and replace this with any number, say x, it still ends up being the same thing, but what you have to keep in mind is that if x is negative, you can never have a negative come out of a square root. So to simplify this, we would have to say, okay, well, this is the number times itself. The only catch is it's not the original number, it's the absolute value of the original number, which means if it's a negative, it becomes positive. If it's positive, it stays positive. That's what this means. It's not true to say that a square and a root undo each other, more that they undo each other and you're left with the absolute value of whatever it was you started with. So here's where the pun comes into play. If I were to pour a root beer, meaning a root beer, into a square cup, would I get just a regular beer? Most people would say yes. As a math major, I say no, you would get an absolute beer. I did this wrong. Hold on, let me do that again. A I don't know why I had root on my mind there. Okay, so if I poured a root beer into a square cup, would I get a regular beer? And according to what I just said, no, you would get the absolute value of a beer. But to keep the pun going, I'm just going to say that's an absolute beer. Because if this was negative, it would have to be positive coming out there. So, that's the first part. Now, the second part here has to do with extraneous solutions. So, let's just say that I have the square root of something that equals -1. In order to find what this something is, what I have to do is square both sides. That's the only way I can lift the radical. So what I'm going to do is take this root, and I'm going to multiply it by itself. What I'm saying is that a number times itself gives me the inner part here. When I multiply them together, I get just this middle part. Let me give you a better example than that. It's too abstract. So if I have the square root of 9, we've already established that's 3. So now my question is, what happens when I take the square root of 9 and I square it? Well, I have to do the same thing to both sides. So when I square this guy, that ends up saying, okay, this not so easy to see. This is a lot easier to see, though. It's just 3 times 3, which is 9. Oh, hey, check that out. They undid each other. We have the 9 here, the 9 here. It's just that when you square a root, you're left with whatever was on the inside there. And that's true for all numbers. So when we're looking at this for all numbers, let's start with a general statement that says the square root of some number happens to be -1. So, to solve for x, what I need to do is start by squaring both sides. That's the only way I can get rid of this radical. So it's going to be the square root of x squared has to be, now what I do to one side of the equation, I have to match it exactly on the other, meaning I'm going to take my -1 and square it here. Well, that ends up simplifying to be, okay, the square and the root cancel each other. This leaves me with just an x over on the left side of the equation. On the right side, that's the same thing as -1 times -1. Well, I've already said that a negative times a negative is a positive, which means this guy ends up being 1. So, in theory, I've found the answer. Whatever this was to begin with, I've now found it to be 1. But let me check my answer here. Let me check my answer. So if I were to plug 1 back into the original equation, this would say, okay, there's that summation symbol again. Try this again. Since x is 1, and I plug it into the original to make sure my answer works, well then I would say, okay, the square root of 1, because that's what x was, I found x was 1, that should be the same thing as -1. What number times itself is 1? Well, that one's easy. 1 times 1 is 1. Anything times 1 is 1. Or anything times 1 is the other number, so it's 1 times 1 gives you the 1. So when I'm looking at 1 times 1 and I simplify, uh-oh, there's a problem here. I've now said 1 is the same thing as -1. But that makes no sense at all. That's like saying, okay, if you have $1 in your pocket, that's the same thing as owing someone $1. Two completely different concepts, right? So that's an example of an extraneous solution. It's when the algebra works, but your answer doesn't. It happens all the time when you're dealing with radicals. So the whole answer that I provided was, if I pour a root beer into a square cup, do I get a beer? No, you would get an absolute beer, because whenever you square a radical, it's always the absolute value. The other one says, okay, what happens if it's an extraneous solution? Well, that's an impossible answer, and when you provide an impossible answer, weird things happen. You end up with like black holes, that's where they say God divided by 0, or with extraneous solutions, obviously, the cup would explode. So, that's the logic behind all of this. Hopefully that wasn't too confusing. I meant that to be a little more funny than it was, and it kind of turned into a dreadful, boring math lesson.